Great. Um, should we start, or will you start?
Yeah, no, I'd be happy to kick it off. Thank you all for making time to attend our workshops today. I'm happy to introduce Jorge from the University of South Carolina, who's going to carry us through the workshops. And hopefully everyone had a chance to register for the site. It's a pretty painless login style to set up your credentials and be able to access the tools for the workshop today. And with that, I'll hand it off to you, Jorge.
Thank you, Cass, and thank you, Melanie, and the whole team that organized this event. I think Melanie put links in the chat window to access the portal, and also was sent to you via email. I will share my screen, and I will go from there. Again, we'll be using a tools. First, my name is Jorge Crichigno from the University of South Carolina. I will open momentarily my cam. And we at the University of South Carolina build some tools that are used by community colleges, universities for training purposes, also for classes. Material include TCP, network protocols and tools, BGP, OSPF, etc. So what we will be doing today is to go over some exercises that might be of interest for some attendees. This website that is here is in your email. Melanie sent this, and one way to log into the portal is by going to this website and clicking on the session. So if you already registered, you can go right away to the portal that we will be using. I will click here, or before I click, also in this website, there are already the update, the slides that we'll be using. So there are 3 sessions. The first one is TCP exercises, second BGP routing exercises, and the third is perf sonar exercise. So the slides that we will be using are already there. Also, these are the same URLs, so you can just click here for the sessions. I will click here. And if I didn't register yet, what I would do is I will complete my name and then my email. And then I will set a password. You set a password and click register. I will not proceed because I already registered. But if you didn't do so, this is the way to register. You will then have to check your email, and you will have to enter a code verification. If you are returning because you already registered, you entered your credentials. Should be logging shortly. Yes, and this is the set of lab. This is a lab library that we developed. It relates to Science DMZ to some extent. For example, you will see tools such as congestion control that are at the heart of Science DMZs, bandwidth delay product, TCP buffers, fairness, rate control, etc. We will not cover all today, but we will cover Eli, who is one of the developers of this lab. We'll be covering 1 or 2 of these labs, specifically TCP congestion control and buffer sizes. So I will switch and then I will come back to the portal. I will switch to the slides for the first exercises. Again, I want to give credit to Eli. Eli is the one who developed this set of labs. And all the lab series, by the way, these labs will be available for 3 months and can be extended if needed. So these labs are referred to network tools and protocols because that's what is covered. The lab series provides learners an emulated environment. This is happening using Mininet and Linux protocol stack. So it helps the students to acquire hands-on skills, performance tools, measurement tools, configuration devices, and we emulate scenarios. So there is a set of labs. We will be doing, I believe, Lab 7 today. Ellie will be doing Lab 7, and we'll be talking about our experience with BBR. We had the experience of using BBR in our Science DMZ. Now, the documentation with each lab includes an overview, and then section 1, all the fundamentals, I would just call theory, and then section 2 to N, this N varies, shows step-by-step directions. And this is literally a step-by-step, and you will get the outcome of the lab. Lab number 1 is about the one that we will show today is about the importance of TCP congestion control. I will give a very brief overview. What are the problems in Science DMZs, high throughput, high latency networks? The traditional congestion control use the additive increase, multiplicative decrease control law. Basically, whenever there is a packet loss, the sending rate decreased by half, and then slowly go back again. For those who are familiar with Science DMZs, you might have seen this figure, and this shows what happened when there is a very tiny packet loss rate. As the round trip times, as the distance between the two devices that are exchanging data increase, the throughput decrease very rapidly. So that's the main concern with the traditional congestion control. So recently, BBR has been proposed. BBR doesn't follow the additive increase, multiplicative decrease control law. Instead, it tries to figure out what is the bottleneck bandwidth between the sender and the receiver. So what we will be doing in this lab is seeing what is the performance difference in an emulated environment. We will modify TCP congestion control algorithm in Linux using the syscontrol tool. We will deploy a wide area network. The network we will set with a capacity of 1 gigabit per second, but we will certainly have latency between devices. And then we will compare what happened if we use Reno, what happened if we use TCP BBR. Reno is a traditional congestion control, is loss-based congestion control. So it's a simple topology, 2 servers, 2 switches. There is a bottleneck of 1 gigabit per second, and then we will incorporate latency. Something else that we will learn in this exercise is the importance of having TCP buffer size large enough. So in many wide area networks, the round trip time is dominated by the propagation delay. What is the round trip time between H1 and H2? So we have to keep the sender busy while the sender is waiting for acknowledgement. So if the buffer size that I'm talking about, TCP buffer size at this point, is too small, basically the sender will be waiting, constantly waiting and wasting bandwidth. So for traditional congestion control, the rule is that TCP buffer size must be greater or equal than 2 times the bandwidth delay product. And this is because of how the kernel in Linux works. Eli might provide more details if you are curious. With the BBR 1 and 2 is something interesting because when we started doing some tests at the University of South Carolina, we tried to use the regular rule, 2 times the bandwidth delay product. And if you do that with BBR version 1 or 2, you will notice that the throughput will be lower than expected. And the reason is because TCP BBR1 and 2, they don't slow down if there are packet losses. They will constantly send as much as possible. And they need more TCP buffer size. There might be losses. We have to keep the sender constantly sending data. So I will switch to Eli at this point. Eli, do you want to share your screen and start with the exercise?
Yes, sure.
Let me close. And again, Eli, which lab is the one that you will be doing so anybody can follow what you will be doing?
Lab 7.
So if you want to follow and do exactly what Eli is doing and seeing the performance, you click in Lab 7 and a pod is a set of equipment needed by the exercise. A pod should be coming. So it might take a few seconds. So Eli, I will stop sharing right now.
Okay.
Trying to figure out, stop sharing. All right.
Can you see my screen?
Yes, yes.
Okay. So first of all, thank you for joining. My name is Eli, and I'm a PhD student at the University of South Carolina. I will be going over Lab 7, which talks about TCP congestion control, and we will see the difference between the loss-based congestion control and the more recent ones, mainly BBR. So what I'm gonna do is first, when you go to the lab, let's say when you click on Lab 7, you see first here the topology. We only have one client, and you see on the top you have the content, and this content here describes the lab. So I will open it in a new window, and I will put it just aside so that we can see both at the same time. So on the left-hand side, you will see the lab manual, and the right-hand side, this is the portal. At the beginning of each lab, we will see a table of content that describes the outline. And then all the labs start with a short overview. What are the learning outcomes and the objectives of the lab? And then we have a section for the settings of this lab. So mainly this section contains information about the credentials. So for example, here we only have one client, client 1. And you will see here we have client 1. The username or the account name is admin, and the password is password. So whenever we're gonna be issuing a command that requires a password, we have to type in the password. Then we will see the roadmap of the lab. So what are the sections? And as Dr. Jorge mentioned at the beginning, we have the first section is always a background, the theoretical part that describes what this lab is about. And it gives the reader, even if he or she doesn't have a knowledge about the topic, they will be able to follow the step-by-step. So I'll not go over these. I will start immediately by the hands-on part, which starts from section number 2. And section number 2 here is the lab topology. So this is the topology that we're going to be using, this lab exercise. We have two devices, two hosts, H1 and H2. H1 has the IP 10.0.0.1 and H2 the IP 10.0.0.2. And then we have two switches, S1 and S2, and we will be configuring the link between S1 and S2 to be 1 gigabits per second. Also, we will see how we can emulate other conditions such as delay and packet losses as well. So the first step is to go inside the client. I will click on client 1, and you will see here that I'm within the desktop of this client. Since we'll be using MiniNet, the emulation tool, the labs have a graphical user interface called MiniEdit, which is really just the graphical user interface for MiniNet. So I will go ahead and double click on MiniEdit as shown in the figure here, figure number 6. And they are asking me for the password. Again, it's in the table. The password here will be password, all low caps. Now I'm in the MiniEdit interface. The next step would be to load the topology. For the set of labs, instead of every time having the user create the topology from scratch, which you can do simply by selecting the components and connect them, we already created the list of topologies for each lab. So if I go to File and Open, we will see here the topologies. I will click on lab number 7 now. Next, before we start doing any measurement, throughput measurement, or any kind of test, we have to start the topology by clicking on the Run button at the bottom left. And once we click on that, the buttons should be grayed out, which means that now the topology and the whole emulation has started. So again, the devices use the network 10.0.0.0/8. And the IP addressing convention that we're using here is that we start by the network address, and depending on the number of the host, for example, H1, it will have the IP address 10.0.0.1. H2 will have 10.0.0.2. If we have more, it's going to be also the same. Now, next, we will start the terminals of host H1 and H2. And really, host H1 and H2 are just network namespaces, virtual, you can consider them as virtual hosts, and we will be using them to perform the test and configure different settings for our experiment. So to start the each host, first we have to right-click on the host and hold the right-click and select the terminal. And what we can see here is the terminal of this specific device. So any command that will issue in this specific terminal will be executed on host H1. And one thing that I want to mention is that any command that you type in here is the same as the command that you type in a Linux device. So basically the same commands that we'll be using here for our test can be used in a production network or in a Science DMZ network. So for example, if I want to see the IP address, I can type in ifconfig, and as you can see, I have 10.0.0.1. This is for host H1. What I'm going to do now is just run a simple ping test from H1 to H2 to see if I have connectivity. So I will type ping 10.0.0.2. And as we can see, we have connectivity between the two devices. I just hit Control-C to stop the test. Okay, so the next step would be to emulate a 1 gigabits per second high latency wide area network with packet loss. And mainly what we will be doing in this section is, I will go back a little bit to the topology. What we will be doing is simply configuring this link here to be 1 gigabits per second, the one between switch S1 and switch S2. And also we'll be introducing packet losses and delays later on the switch interface S1-ETH2. So I can emulate delay or packet losses on this interface so that I can get a more realistic test. And also I will be changing the link capacity to 1 gigabits per second. By default, all the other links already have large capacities. For example, if you don't change anything, they can go up to 45 or 50 gigabits per second. Okay, so I will go back to where we were at section 2.2. And to emulate the packet losses and to change the link capacity, we have to go to the terminal. And this terminal is the whole host terminal, which is client 1. So we are not issuing the terminal of any of these devices. I'm issuing for the whole host. This is the terminal on the desktop. And then we will be issuing this command, which allows us to configure the packet loss through netm. And netm stands for network emulator. It allows us to emulate various conditions in our network. Before we issue this command, I want to point out that you will see here one of the labs is dedicated to netm, lab number 3 for latency and jitter emulation, and lab number 4 also for packet loss and duplication. So all these commands are explained in detail in those labs. So I will start by typing this command, sudo tc for traffic control, and QDisk for queuing discipline. Add for the device S1-ETH2. So I'm adding now a new queuing discipline to S1-ETH2, which is the interface of our switch 1. I will add it to the root, meaning that that will be our first queuing discipline, and I will give it a number 1. By giving it a number, we will be able later to combine multiple queuing disciplines. And then we have to specify what a queuing discipline that we're going to be using now. I will be using netm to emulate packet losses. So netm, network emulator. And here you can write loss, latency. You have a lot of parameters that are discussed in the other lab. But for now, we're just going to emulate 0.01% packet loss. Hit the enter, and now they're asking us for the password, which again is password, all shortcut. So we just emulated 0.01% packet loss on S1-ETH2. Now, the next step is to modify the bandwidth of the link connecting the two switches. And we're going to be setting it to 1 gigabits per second. We will be using the following command. So for this queuing discipline, it's called TBF, the token bucket filter. And also, we have a lab dedicated to that, which is lab number 5. So sudo tc qdisk add device S1-ETH2. So I'm adding to the same device now, and I will use parent 1. This means that I want to connect the current queuing discipline to the one that has the number 1, which is in our case netm. Handle 2, so I'm giving it a number in case I want to add more later. And then we specify the queuing discipline type, which is TBF for token bucket filter. Token bucket filter will allow us to specify the rate, which is the link capacity. I will use it as 1 gigabit. The burst parameter, we will use it 500 kilobytes for this test. And the limit, which is very important, the limit is really the router's buffer size. So here we are talking about the buffer size on the switch S1 here. So we are changing the buffer size. The value that we are using for this test is 2.5 megabytes, so 2,500,000 bytes. And what I did so far is that I added 0.01% loss emulation, and also I configured the link to 1 gigabit with a 2.5 megabyte of buffer. Dr. Jorge, shall we take questions? Shall I pause for questions, or shall I continue and keep questions for later?
I don't see questions.
Okay.
But yeah, sure.
Okay, thank you. I will just proceed, and in case there's any question, we will be answering at the end. Okay, so next, I will skip section 2.3, and this is just to test the connectivity. What we're gonna... Sure.
First, I'm listening echo, but also there is an observation from Mark. I think the speaker may be going through all this too fast. So okay. Just try to keep the pace so anybody can follow you.
Sure. I will slow down. Okay, so again, so far what we did is we configured 0.01% packet loss on the switch S1-ETH2 interface to emulate losses, and we configured 1 gigabit link capacity from S1 to S2, and we configured the buffer size to be 2.5 megabytes. Next, I will skip the section 2.3, and I will go immediately to show how we can add latency. So what we've done so far is we simply added losses 0.01%, but in a more realistic wide area network, we will have high latencies, 20, 30, up to 100 milliseconds. So how can we do that? How can we emulate it in our mininet environment? So currently I'm doing this section 3.2, and we will be executing this command, which really simply just changes the queuing discipline that we had, netm lost 0.01%, to have, in addition to that, a delay of 30 milliseconds. So to do that, we will type in sudo tc udisk. Again, now we are configuring a queuing discipline. But now, instead of adding, because we already have that queuing discipline, we will issue change. So change allows us to change if we have any queuing discipline already configured. Then we specify which interface, which is S1-ETH2. And I will be changing this command, so this queuing discipline, right? The one that deals with losses, just to include delay. So we have to type in exactly the same command that we did before, root handle 1 netm. I will rewrite the loss so that we keep the loss configured, 0.01%. But now we will include a delay. So by the way, when you start typing any of those keywords, if you press the tab, it will help you with auto-completion in case you forgot the syntax. So we added 0.01% loss. Now we'll be adding 30 milliseconds of delay. Once we execute this command, we are really changing from simply loss to loss and delay.
So Eli, in order to, if there is anybody who is following, I will just pause for a second here. But meanwhile, what you are doing is you are just working always over the interface of the switch that is facing the other switch. So,
yes.
So if you want to show the topology where you are working.
Sure. All these commands that we've done, these 3 commands, are executed for this device, S1-ETH2. This is where we specified that you can see S1-ETH2. That's the device. So we are adding 0.01% loss. We're adding 30 millisecond delay here, emulation. And we are changing the rate so that we have a link of 1 gigabits per second between switch S1 and S2. Also, we changed the buffer size here to be 2.5 megabytes on switch S1.
So basically, this could be a good way also to test the impact of the router's buffer size, or in this case, the switch buffer size. So if you have too little of a buffer size, you will see a lot of packet losses, right?
Yeah, exactly. We need to make sure that we have the right amount of buffering. Very small buffer will hurt the link utilization, and very high buffer will affect the latency that we have. So, and this whole idea of buffer sizing, we have a lab for it, which we will go over it after we finish this one. We will show the difference between the different settings of buffers. Okay, so I will go back to the section where we were. All right, so after we configure the loss, the delay, and the link capacity, we will modify the TCP buffer size. And this is the buffer size that Dr. Jorge was talking about in the presentation, the TCP send and receive buffers. And those are very important to be modified so that we can achieve good throughput, high throughput. We have to make sure they are high enough so that we can get that throughput. And again, for loss-based congestion control, there should be at least 2 times the bandwidth delay product. For BBR, it should be considerably larger than 2 times the bandwidth delay product. So to modify those buffer sizes, we have to make sure that we execute them on the right terminal. So we want to modify the buffer size for the host H1, and therefore we have to go to the terminal of host H1 to issue that command. And this command here, sysctl, system control, it allows us to specify some parameters that are in the kernel. So this parameter here, net.ipv4.tcprmem, is configurable. It's a Linux kernel parameter that you can change. And the sysctl allows us to override those settings. You can, for example, change the congestion control through that. You can change other kind of parameters. So we have the send and the receive buffer. We will change them to make them large enough. And we have three values here. The first one is the minimum. The second is the starting one. So this is the starting buffer that will be used. And the maximum would be the last value here. So I will go ahead and type in this command in H1, sysctl-w, because we are writing net.ipv4.tcp_rmem equals to, we specify the values. And I will also use the up arrow to load the previous command and simply change rmem to wmem. Those are both the send and the receive windows.
So, Eli, you have a character there that is wman equal, and then you have another character. Which character is that? In case that, because it's not that clear.
Yeah, this is the single quote.
Single quote, okay.
Yeah. And we have to make sure we don't have spaces after wmam or rm. So always when we write those commands, when we specify the parameter name, immediately equal and then the value. We shouldn't have spaces here. Okay, so I entered these two commands on host H1. We have to do the same for the other host, for host H2. So I will go back to mini-edit, the graphical interface, and launch the terminal of host H2. Right-click on H2 and terminal. And from here, I will again type in the same command. So sysctl-w net.ipv4.tcp_rmem equal single quote and then the values. And we close the single quote. IPv4. And then we will do the same for wmem. Okay.
So you use the third parameter, 15 million, I believe, or what is the number there?
So this number here is 150 megabytes.
150 million.
Yeah, just to make it large enough.
So that third parameter is the parameter that defines the TCP buffer size.
Yes, yeah.
Yep.
All right, so next we will see how we can change the TCP congestion control algorithm in a device. And again, those are the same commands that we can use in a regular Linux machine. So on host H1's terminal, we will change the TCP control to Reno. So I will go back here and click on the terminal of host H1. And changing the congestion control is also a sysctl parameter. So sysctl-w for writing net.ipv4.tcp_congestion_control equal. And here we specify the congestion control that we're interested in. For example, in our test, we will be using Reno, a loss-based congestion control. And once we see this output, it means that we successfully changed the congestion control to Reno. Next, we will go to host H2's terminal and start an Iperf 3 server. Iperf is a tool that allows us to test the throughput between devices. It also reports other metrics such as the round trip time, the congestion window, and other stuff as well. So it works in a client-server approach. We start a server. For example, here I'm starting an Iperf 3 server on H2. This will be our receiver. And then we will start a client on host H1. So now I will go back to host H1 and continue from here. Now I will be executing this command, mkdir Reno and cd Reno. So I'm creating a directory called Reno and navigating it to that directory. And then we will start the test by using the Iperf 3 client. So Iperf
So,
3.
so do you want to make a pause, Eli, just in case that people are following you? I think
Sure.
just to give a little bit of time. So for those, I think this was a an observation in one of the presentation, in the past presentations. These congestion control algorithms are by default already in the Linux kernel. How about others that are new, like BBR or BBR version 2?
Mm-hmm. Yeah, so by default, as you were saying, you have Reno, Cubic, a few congestion controls are activated. However, in case there's a new congestion control that is not there, you have to load it. You have to load its kernel module. For example, to do that, you would use modprob command, and then you specify the module name. For example, for BBR, it's going to be modprob TCP-BBR, right? For other congestion control, you will have other ones as well.
So it can be easily updated basically with one command.
Yes, yeah, for sure.
All right.
Next, so I will continue by issuing the Iperf 3 client command. Iperf 3-C, C means that we are running Iperf 3 as a client now, and we have to specify the IP address of the destination. In our case, host H2 will be the receiver, the server, and it's listening on port 5201. So what we're gonna do now is we're gonna specify the IP address of that host, which is 10.0.0.2. Also, we can specify parameters such as how long this test will gonna be executed. By default, Iperf 3 executes a test for 10 seconds, but we can change that using the -t. -t30 means we are running it now for 30 seconds. And then we have an option, -j. -j allows us to export the output of this test to a JSON file. And JSON file is just a data representation type that allows us to easily interpret the results using a certain program. For example, if you want to plot the results, it would be convenient to export the results through a JSON output. And finally, we are redirecting the output, the standard output, to a file called reno.json. I hit the enter, and now the test has started. It's going to last for 30 seconds. We can see the output on host H2. But meanwhile, of course, the output also will be written to the file on host H1. As we can see so far, although we configured the link capacity to 1 gigabits per second, the throughput is much lower. We are around 200, 300, 100 megabits per second. And this is because of the losses that we emulated and the problem of loss-based congestion control algorithms. Then we can use a script that allows us to plot those, plot the result of these tests. For example, if I want to see the throughput and the round trip time, we can plot them. So plot_iperf.sh, and we give it the name of the file that that was exported from our test, which is reno.json. And once we click on that, and once we execute this command, a new folder results will be generated. Then we will navigate into that folder, cd results. And here, if I use ls to list the content directory, you will see that we have PDFs generated for the amount of bytes transferred, the throughput, the round trip time, congestion window, retransmissions. So you can see how that test performed by just opening these files. So for example, if I want to see the throughput, I'll use the command xdg-open throughput.pdf. And as we can see, I will maximize. We see a graph here where the x-axis is the time in seconds. We run the test for 30 seconds, and hence you can see we have from 0 to 30. And the y-axis here is the throughput in megabits per second. So we know that the link that we configured is 1 gigabits or 1000 megabits per second. However, we were not able to fully utilize that link due to the losses that we emulated and the high latency, and also because we are using the Reno loss-based congestion control algorithm. So we can see that the throughput is around 200, it goes up to 300 and then goes down, but it never achieves the 1 gigabits per second throughput.
Ellie, there is an observation. Could you show where the plot utility is? Because we're missing plot utils. That's the observation. How to plot again the result.
Sure. So I will. So I will go back to. I will go one step back in the folder to Reno. I will use ls, and here you can see that we have reno.json. This is the file that was exported from the Iperf test. And here we can issue this command on the left-hand side, plot underscore Iperf.sh, and then write reno.json. This will generate the files for us. And I want to mention also that this tool is, you won't find it in a regular Linux device, even when you install Iperf. This is a tool developed by us, but you can always copy it from this machine. And also it's available on GitHub if you are interested and you want to use it on your own machine as well. All right. And also there are other outputs that were generated, for example, the congestion window. We will not plot that, but it's the same idea, xcg open congestion window.pdf, and you will see the evolution of congestion windows throughout this test. Okay, now what we're gonna do is we're gonna stop the server, the Iperf3 server on host H2 using Control-C. And then we're gonna go back to the home directory. So here it shows cd ... meaning I want to go 2 steps back, but because I already went 1 step back to show plot Iperf, I go only once here. So basically, if you are here, it means you are now in the home directory and you can proceed from there. Now we will repeat the same experiment, but instead of using Reno loss-based congestion control, we will see how we configure BBR, and we will see the difference in the performance. So again, on host H1, we will change the TCP congestion control to BBR. Sorry, sysctl-w net.ipv4.tcp congestion control equal to BBR. Okay, and that's it. So now instead of using Reno, we are using BBR. Again, we will start the Iperf3 server on host H2.
Ellie, do you want to pause and go to the command again, just in case somebody's following you? The command to change the congestion control. And so you are changing on both sides or just in one side?
In this case, we are only changing on one side, on the sender side. But if you want to do that on H2, it's the same command, nothing will change.
Yeah. So the sender side is the one that is at the end of the day selecting the congestion control.
Right.
Or BBR.
Yeah. And that's because H1 is really the device that is pushing the data. Okay. So on host H2, we will start again the Iperf3 server, Iperf3 --s to start the server again. And then we will repeat the same steps. So we'll create a directory for BBR on H1 and navigate into that directory, mkdir BBR and cd BBR. Again, we just created a new folder, BBR, and then we are changing the directory into that directory or that folder. The next step is to start again the test. Same thing exactly as we did before. Iperf3-C, the IP address of the host H2, 10.0.0.2. The time, we will also run it for 30 seconds. JSON output, and now we will redirect the output to a file called bbr.json. Okay. And after we write this command, I will hit on enter to start the test. Now, as we can see already now in the output of H2, we can see that the throughput is much higher. It's around 950 megabits per second, which is really the maximum that you can achieve, because even if we configure the link to be 1 gigabits per second, we will not achieve it regardless of the congestion control. But those small amount of bits that are left, this is normal. If you are getting anywhere in the 900 megabits per second, means that we are really fully utilizing the link capacity. Okay. I will shift back now to host H1. And as we can see, after the test finishes, the prompt will appear again so that we can type in a new command. Also, we will generate the plots for this JSON file. So plot_iperf.sh bbr.json. So similarly, we have now a new folder called results that contains all our graphs. Let's navigate into that using the cd command. Cd results. And here we will see all these different PDFs. If you want to see the throughput for this test xdg-open throughput.pdf. Okay, so again, this is the same graph. On the x-axis, we have the time, and the y-axis, we have the throughput that was achieved for this specific test. And as you can see, with BBR congestion control algorithm, even when we have losses and we have a high latency, in our case, we use 0.01% loss and 20 millisecond latency, we are still able of achieving more than 900 megabits per second on average. This means that we are really almost fully utilizing the link capacity, which is configured to 1 gigabits per second. Now, those spikes that you see are based on the dynamics of BBR. This is normal. Every 10 seconds, you will see a short spike like this. But really, if you just average the values over time, you will get more than 930, something like that, around 930 to 960 megabits per second. And also, you can see the congestion window. So if you want to see that, XDG open congestion window, and you will see the evolution of this congestion window over time. So that's it for this lab. So as a summary, what we've seen is how we can emulate packet losses, how we can emulate latency, how we can change the link capacity. And then we saw how we changed the TCP send and receive buffers, which should be enlarged to be able to get good performance, high throughput. Also, we saw the way to change the congestion control algorithm in the kernel, and we compared the throughput of a loss-based congestion control, which is Reno in our case, versus the new congestion control, which is BBR. And we've seen that BBR was capable of achieving very high throughput, even in the presence of packet losses and high latencies.
Thank you, Lee. And just to be respectful of the agenda and the attendees' time, we are at 1:50 p.m. right now, Eastern.
I have a question.
Yes.
So the BBR, I know you implemented that in TCP, and your client are the Linux operating system. In the current production right now, do you think we have BBR already implemented with TCP, or do application developers have to update their TCP stack?
In the recent kernels, it is there. However, you have to import it. So, for example, let's say I'm on host H1 here, and I use sysctl net.ipv4.tcp congestion control. Here it shows us what is the one that is currently configured. I believe if we go to the terminal of the whole machine and we write here sysctl net.ipv4.tcp available congestion control, this will show you what are the available congestion control that are loaded in your kernel. In our case here, we have Reno, Cubic, BBR, and HTCP. However, if it's not there, then you have to just simply use modprob, and then the name of the module. I believe it was TCP-BBR. By doing that, you are loading now the BBR kernel module, and then you'll be able to see it in your available congestion control.
And then you can tweak it, change it from the default to this BBR, right?
Yes, exactly. And one more thing that I think we should mention is that if you change it using sysctl like this, it's going to be temporary just for your session. However, if you want to make it permanent, you can go to a file called etc/etc and sysctl.conf. You can use any editor. I'm using VI here. But basically, what this file contains is all the parameters. And let's say you want to always use BBR, then you would write here the key and the value. So for example, net.ipv4.tcp store congestion underscore control equal to BBR. If you write that and then you save your file, you reboot, then by default, your congestion control will be BBR.
So I'm guessing to do this in the Windows platform, we have to do the modify the registry, right?
To be honest, I've never tried that on Windows. I'm not very familiar, but I'm guessing that, yeah, probably in the registry, it should have some key that can be changed.
Thank you.
So let's see if there is any other question, Eli. I think just to try to keep on time with the agenda, this will be the TCP exercise. There was another exercise that we were planning, which is the impact of the buffer size of the router. Which lab is that, Eli, if in case of somebody wants to do it?
Sure. It's lab number 14. It's called routers buffer bloat. So just a quick, really a quick overview of what this lab is about. This is the topology for lab number 14. And the idea is to show the user the impact on the buffer configuration that you have on your switch or on your router. So this lab will show you, for example, if you use a very small buffer here on S1 ETH2, and you run your test, you will see that you will get very low throughput. But then you would say, okay, I'm gonna enlarge that buffer to a very large value. Well, if you do that, then you will see that you will have high latency if you try to ping, let's say, from H2 to H3. So really, the right buffer is still an open question. It's not something that is completely understood so far, but there's a rule of thumb that says that the router's buffer should be equal to the link capacity multiplied by the average round trip time, or what is referred to as the bandwidth delay product. This one holds if you have small number of flows, and even when you have large number of flows. However, also in the literature, it was shown that you can further reduce the buffer size to bandwidth delay product over the square root of the number of large flows. But basically, even the bandwidth delay product will work when you have large number of flows. So it's a nice lab that really shows the impact of changing this buffer from small to medium to large.
Great. So thank you, Lee, again. I think Cass, if you consider convenient, why don't we have our break for a few minutes, maybe 10 minutes, and then we come back?
Yeah, that works fine. So we'll all come back at 2:05. Thank you all.
Thank you.
Thank you.